And thanks to Terry and Jenny and David for allowing me the opportunity to come and talk to everyone here today. I'm going to give you a brief overview of some work that I've been doing over the last couple of years from various locations, looking at how water temperature is actually influencing the food intake of fishes and how that might play out into ecosystem functions. So temperature is a fundamental environmental parameter in marine systems, and as Ove pointed out last night, increasing temperature is one of the four major threats facing coral reefs. Whilst Jeremy highlighted another major one, and perhaps more important, is overfishing, we're still, temperature is one of those important drivers that we're seeing. And there's been a lot of work looking at the effects of increasing temperature on both benthic communities and fish communities, ranging from the individual up to the community, larval development, and so forth. We've also looked, or quite extensively looked, at the effects of climate-induced habitat degradation and their effects on fish communities. One thing that's largely escaped our attention to date is the opposite direction in that flow, so the effects of the fish themselves back on to the benthic community. So how increasing temperature is affecting their feeding rate, their intake, and what that plays out in the benthic communities. Now that's important for energy flow and key processes such as herbivory, highlighted by Jeremy and Dave this morning. Like all ectotherms, fishes, the biochemical and cellular processes are largely dictated by temperature. So when we get increased temperature, we'd expect that they've got an increased energy demand. Now how they deal with that will depend on whether they're actually going to increase their food intake or reduce their energy usage, so slow down their activity patterns and so forth. So first of all, I'd like to take you to one area of the world, the Arabian Gulf. In the last couple of years, I've had the opportunity to work over there, and most people see this environment as one of the world's warmest reefs, and yes, it is. In summer, it gets up to 35 degrees quite commonly, sometimes up to 37 degrees. But the other thing, when I started working there, I didn't actually realise it gets really, really cold. In winter, it gets down to 15 degrees, and we've actually got some temperature loggers out on the reefs off Abu Dhabi at the moment, and it got down to 12.8 degrees last winter. Okay, so you're getting over 20 degrees of variation in a single 12 months. Now, I know most people from North Queensland are actually suffering down here at the moment, but that's nothing compared to what these fish are dealing with on a yearly basis. So I just want to move on. A lot of this is, the information I'm going to present to you today is just based on feeding observations of individual fishes. So you follow them around for 3 to 5 minutes, you record what they're feeding on and how often they're feeding. So this first figure up here is for a parrotfish in the region, Scarus persicus. It's nominally herbivorous. And the two things that you can see there is the feeding rate on the y-axis and the fish size across the x. And one thing that will stand out is that feeding rate generally declines as the fish get bigger. Reasonably straightforward. I'll also point out that I didn't go there when the temperature was 13 degrees or 15 degrees. I'm a bit of a wimp, so 23 degrees is pretty much my limit at the moment. But what happens when we actually go back in some of the warmer periods, we get this dramatic increase in the actual feeding rate in these systems. So for around about a 6 degree Celsius increase in temperature, we're getting a 70 to 100% increase in their feeding rate. Okay, so that's for one benthic feeding fish. If we move across and look at a pomacanthid or an angelfish, Pomacanthus maculosus, this one is super abundant within the Gulf. I've never seen so many pomacanthids in my life. Again, we see that dramatic increase. This time it was an 8 degree change in temperature from around 20 to 23 up to 30, 31 degrees. One thing to note on the lower side is there are a lot of fish that effectively cease to feed during the winter or the cooler months. Rapidly picks up as we go into summer. And again, for an 8 degree increase, we're getting a 100 to 200% increase in feeding depending on fish size. And the final species I'd like to look at in this area, and now I've removed size from this figure because they're largely all adult fishes. Okay, so they're very limited size range. We're looking at 10 to 11 centimetres primarily. And again, you see that feeding rate increasing from 18 to 23 to 29, but interestingly, once we get up to 33, we're starting to see it drop off slightly. Now, whether it's getting to its physiological limits or whether there's a trade-off in the energy demand, how much they're actually getting from that extra feeding and the cost of actually moving around to get that prey. So that's for further investigation. So they're all benthic feeding fishes. So what about some other types of fishes? Now, Morgan introduced this last night, and I was involved in some parts of this project in an experimental setting where we got coral trout from two populations, one in the northern GBR, one in the southern GBR, brought them back to JCU, put them in 4 temperature treatments, 24, 27, 30 and 33 degrees, acclimated them for several weeks, and then measured just about everything that we could on these fish, one of which was feeding. So what we see there, again, is we get this increase in food intake with increasing temperature. Now that's just expressed in percent body weight as far as the food intake goes. But also, as Morgan mentioned last night, is that there was some sort of trade-off. So activity patterns actually decreased with increasing temperature. Their swimming speed inside those tanks actually dropped off. The two lower temperatures were very similar, but once we got to 30, 33 degrees, it dropped off quite markedly. And the time resting, now it's the time that they just spent sitting basically on the bottom of the tanks, actually increased with increasing temperature as well. So what does all this mean? And I'd like to just bring this back to an example, again, following on from Jeremy and Dave, the importance of parrotfish in reef systems. So just using an example as we move down the east coast of Australia from the northern GBR down to the central, southern, and then to the subtropical reefs of Lord Howe Island, Elizabeth and Middleton reefs. Now that's the summer temperatures there, 29 to 30 degrees down to 24 to 25 degrees. Okay, it's a large gradient. But again, if we look at the feeding rates of these parrotfish, and here we've got Pleurotus sordidus, which is generally a small excavator, grows to about 40 centimetres in length. And we get that similar pattern with decreasing temperature. Okay, the actual feeding rates are dropping off. If we look at other groups, so at the top, Pleurotus microrhinus gets to about 80 centimetres, a large excavator, has a lot more impact in terms of bioerosion, and also a scraper down the bottom, Scarus frenatus. We're seeing a consistent pattern all through these, that we're getting that decrease in feeding rate as we're moving down the coast. So what does it mean? If we actually look at just straight biomass, the biomass of these parrotfishes across these reefs is remarkably similar. This is based on 3 reefs in each of those 3 locations, a lot more variable in the southern area, in the subtropical region, but generally we've got quite a high biomass as we move across. The key thing about parrotfish is that you actually go out and measure their bites. You can measure the area that they're scraping with each bite, and you can measure the volume of material that's removed with each bite. So we can scale up to a feeding impact, fish density times feeding rate times the area or the volume. And just lastly, to finish off, if we actually do that, here we've got grazing on the left and bioerosion on the right. That pattern, if we had have inferred it from biomass alone, has dramatically changed. So we're actually decreasing grazing rates quite dramatically as we're moving into those cooler waters. Bioerosion drops down as well, but not quite as dramatically, and that's largely because those larger fish didn't seem to be as sensitive to that temperature change. And with that, I'd like to thank everyone that's been involved in this work. Thank you.